Hello and welcome to our last example on application of principles of fluid statics and pressure and so forth. This one is strictly algebraic, and the problem is to find a formula for gauge pressure in a small, that's a key word, spherical drop of water with surface tension of sigma, so whatever the surface tension is. So there's our problem statement. I think we will find a sketch somewhat useful. So here's our drop of water, making it look spherical by those little markers there, and it has some radius r. So here's what we know. We know it has surface tension. We know there's some diameter associated with it. We know that it has a radius r, and we're told that it is small. Okay, the small is going to figure very important soon. Unknown. Pressure gauge is some function of surface tension, and I'm going to choose diameter. We want to find the function, or at least the functional structure. That's about all we can do. Governing equations. We know that we have sum of the forces, mass times acceleration. We know that the force of surface tension is 2 pi r sigma, and that happens to be equation 2.24 of our book from a while back. And we know that the volume of the sphere is 4/3 pi r cubed. So let's go ahead and find a solution. We'll find that a particular free body diagram will come in handy. I'm going to cut that drop in half. So there's my drop sliced in half through the miracle of drawing. Introduce my coordinate system, x and y. And we know that this drop height right here has a diameter of d. Okay, now here comes an important assumption. dp d along this axis, I guess dp dy, is small. So we're going to neglect vertical variation in pressure. Now this only works because it's small. We're basically, maybe we're moving a millimeter up or down in the fluid, and it's, it has to vary, but it's not going to vary very much. We might not even be able to measure it even with modern tools. Okay, that key makes the rest of the problem quite simple. We'll look at the sum of the forces in the x direction. Let me divide this so there's no confusion. There we go. I'm trying to fit this on one page. It's not going to work, so I probably should have just moved. Mass times the acceleration in the x direction. That's going to be set to 0. So what are the forces? Well, I don't even have all my forces drawn. That was a mistake. Forces in red. So this is the tensile force from the surface tension of the drop, and then there is some pressure force from the other half of the drop pushing it in. So we have F sub P is in the plus x direction minus F sigma in the minus x direction, and that equals 0. From that we conclude that Fp equals F sigma. Therefore, force of pressure equals pressure times pi d squared over 4. So that's pressure. This is area. F sigma from the formula is pi d sigma. We have 2r, which is the same as the diameter. And now we will equate the two. We have this force balance here, and we can use that to find the formula in terms of pressure. So we have P times pi d squared over 4 equals pi d sigma. My green canceling pen. Pi's go away. That diameter takes care of one of those. And so what we'll do is we'll move the 4 over to here, and we'll move the d over here. And we come up with pressure is equal to 4 sigma divided by the diameter. And that's our solution. Not a very interesting function, but it is a function nonetheless. Quick discussion. Problems of force balance. If we fail to recognize that, we won't get anywhere. There were no numerical values. It strictly was an equation producer. And we could examine dp dd equals minus rho g to decide how small is small. Okay, because there has to be some variation, but we don't really know what it is. And doing part 2 is kind of outside the scope of this class. All right, well that concludes this example.